Be led by Chris Budd from the University of Bath, who's going to talk about Monge ampere-based moving mesh, which I know nothing about, so he's going to enlighten us.
Well, it's a great pleasure to be here. I'd like to firstly thank the organisers for organising both this meeting and the programme. It's looking like it's going to be an extremely exciting programme, and I'm very much looking forward to taking part in it. I was one of the very first people to come into the Isaac Newton Institute when it was built. We had, I think, the first ever conference we were at, so I feel I know this place very well. Anyway, I'm going to talk about something which is a bit different from the talks that we've had already on adaptive meshing, in that I'm going to give a talk about moving meshing. So it's a rather different approach to adaptivity, but I hope I can convince you in this talk that it's a valid approach and something that we should consider very seriously. And this is joint work with a couple of colleagues at the Met Office. We heard Chiara yesterday talking about data assimilation, and also with two postdocs who were on knowledge transfer grants joint with the Met Office. This is very collaborative work with the Met Office. So what do we want to do in adaptivity? Of course, what we want to do is we want to capture small scales. That's our basic objective, and that might be because we want to resolve small scale features like storms or clouds, or, as we heard from Chiara yesterday, maybe want to avoid spurious correlations when we're doing data assimilation. So there's lots of good reasons to want to resolve small scales. And what we've heard in many talks is about the use of adaptive mesh methods, where you typically add in points where you want extra detail or take them away where you don't. However, an alternative way of doing adaptivity is to always work with a fixed number of points in a fixed topology and simply move them around, and the idea is that you try to move your points so that you kind of optimize the errors that you're going to get from your computation or the resolution that you're going to get. So it's a sort of different approach. I'm always going to work with the same number of points, but I'm going to move them to where I want them to be useful. And these sort of methods, which are generally called R-adaptive methods, relocation adaptive methods, have a number of really kind of nice properties. One is, because you're always working with a fixed number of points and your topology is always the same, it makes all the kind of internal structures of your codes very, very much more straightforward. You don't need to worry about reassigning work and balancing things like that. And that also means that you can couple an adaptive mesh very easily to a standard CFD solver, because your data structures are always the same. So those are kind of computational reasons. Another reason is that if you're moving nodes around, there's a really good chance that you can essentially capture underlying physics in the problem. So if you have a Lagrangian structure like a moving front or a singularity developing, then the points can move along with that. If you have symmetries in the problem, continuous symmetries, scaling symmetries and so on, then the points can move with those. Associated with symmetries are conservation laws, so you could get conservation laws for free, and you can pick up self-similar structures, and that's all very useful. So these are good mathematical reasons. And another reason I really like our adaptive methods is that you're working with the whole mesh in one go. You're not working with little patches here and there. So you've got actually very good control over the entire regularity of the whole mesh, rather than just worrying about bits here and there. So I think these are really nice features which make these methods well worth pursuing. But they tend not to be very popular, particularly in meteorological applications. And here are a couple of, three reasons why they've not been popular in the past. One is the curse of mesh tangling. As your points move around, particularly if you've got high vorticity, it's very easy for the mesh lines to then tangle up with each other, and then you get nonsense. If you don't tangle, there's always the problem you get skewness, where you get long, thin triangles developing, and obviously you want to avoid that. And also, they've been traditionally very hard to use in 3D. Again, tangling is particularly a problem in 3D. So here are reasons why they've tended not to be popular. Yes?
You said you don't change the topology?
Don't change the topology. Topology always stays the same.
Definition of R adaptive, or is that a constraint?
Well, I'll show you how it works. It'll become obvious. hopefully, in my approach to it anyway. So what I'm going to actually do in this talk is talk about a particular method of our adaptivity, which is based upon ideas in optimal transport theory, developed by people like Brené and so on, and Mike Cullen himself at the Met Office, and show how we can do very effective R adaptivity by solving a certain set of equations called the Monge ampere equations. And this leads to a very nice method, which is fast, robust, and effective. And one of the key features of this is that we can prove rigorously that you avoid any problems with mesh tangling. You can also prove, get quite good estimates on the skewness of the meshes to show that you actually get really quite regular meshes. It's a method which works as well in 3D as it does in 2D or in 1D, and it's a method which can be quite easily coupled both to CFD solvers, and we saw with Chiara's talk that it can be incorporated into data assimilation codes as well. So there's a lot of nice features about these sort of methods. So just to quickly give some literature, moving mesh methods in atmospheric flows or meteorology are not particularly new. And here are some very nice papers, Seniceris and Howe. Mocha wrote a very seminal paper I felt in 2001. If anyone's interested in the particular approach that I'm going to talk about, I wrote a long review article with Bob Russell and Wei Zhang Huang in Acting Numerical in 2009, although things have moved on a long way since, and my most recent paper, which hopefully will appear fairly soon, is that one there. Okay, well, let's address the problem you raised and to show you what I'm trying to do. So the way I think of our adaptivity is not to think in terms of meshes at all. I think of it in terms of maps. So basically, I have some domain. I shall call this the computational domain, and I'll always call that omega c. And whilst I'm going to draw it in as a two-dimensional thing, this could easily and generally will be a three-dimensional thing. And in this domain, I put down an extremely nice, simple, uniform mesh. Could be uniform triangles, uniform cubes, uniform squares, whatever. So that's my topology. So I define my mesh topology in the computational domain. And then I have a function f, which is a function of time, which maps that domain into the physical domain. Here's the physical domain, and this is where your equations sit. So this is where your Navier-Stokes equations or the Euler equations or whatever you want to do sits in that physical domain, and all your equations are posed in this domain. And then we get a mesh in this domain, which is the image of the completely uniform mesh in the computational domain. And just to make notation easy, I will use Greek letters for anything computational, and I shall use Roman letters for anything physical. And all my computations are going to be done over here. So as far as the computer is concerned, all it ever sees is a completely uniform mesh with very straightforward topology, no hanging nodes, connectivity very easily sorted out, and all the addressing and all that sort of stuff sorted out. What the physics sees is something where you might be pushing mesh points where you need them in order to resolve your small scales. So that's the kind of basic idea of our adaptivity. It's all in the function here, and we can get properties of the mesh, regularity properties of everything by looking at the underlying analytic properties of this function here. So how do we do it? Well, the technique that we use goes right back to de Boer, and it's the technique of equidistribution. And we've kind of already seen this in the AMR presentations earlier, in that I'm going to have a measure m, a time-evolving measure, and basically m is going to be large if I'm interested in concentrating my points there. So it could be a measure of the error of the solution, or it could be something else, but something which drives me to want to concentrate my points there. And then I might have some sort of unit set in the computational domain, and my function f from that to the physical domain maps that to some sort of distorted set. And the idea of equidistribution is that we try to keep the integral of this measure over this image set constant, regardless of the where that might be in the domain. If I have a unit set, a unit cube in my computational domain, the image of that is this distorted thing. I'm going to always try to equidistribute this measure here. And one of the reasons for doing this is that if you equidistribute this, it basically minimizes its maximum value. So if we're talking in terms of error, if we equidistribute this error over the whole domain, it minimizes the maximum value that error can take. So that's a very powerful result there. So this is the basic idea. As I say, it goes way back to Du Bois, who was interested in using it for approximation theory and devising good meshes for approximation. It was then used in the two-point boundary value community, looking at one-dimensional meshing, and now we can use it for three-dimensional mesh adaptation as well. So there's the equidistribution equation. Now we don't actually work with that, we differentiate it, and if you differentiate it, and this is the Jacobian of the map from computational space to physical space, then the equation becomes this, and that is the equation which is the primary equation for defining the map that I have from my computational to physical space. So this function m here, this is something you know. It's something that's kind of God-given or numerical analysis given or physicist given. It's something you know, and then you have this Jacobian which you're controlling in terms of this, and then you want to solve that. And of course that's a really nice, highly nonlinear equation. I like nonlinear equations. Okay, so God is in this function here. Everything depends upon this. And what you want to do is to choose this function m, as I say, to concentrate points where you need them. You also, as well as concentrating points where you need them, don't want to starve other areas of the domain from points where you probably need them as well, but not in such great density. Okay, so that's the approach we're going to use. And just to say, this is a very general approach because any transformation from a computational to a physical domain has underlying it one of these functions here, and that goes right back to Radon and Nikodym and the Radon-Nikodym theorem. Now, when we had the discussion yesterday about what we should be doing for the next 4 months, one of the things that I raised was what's a good indicator? What's a good way of defining where you want to put your mesh? And the same question comes up in AMR as it does in our adaptivity, and basically boils down to what should drive the choice of this function here. And there's lots of kind of ways of doing it. The simplest is to kind of use some sort of physical reasoning to say, well, this is where we believe we should be concentrating points. And so from a meteorological point of view, potential vorticity or something closely related to potential vorticity, it turns out very often to be an extremely good choice. Chiara Piccolo in her talk yesterday was using a form of potential vorticity as her monitor function. Another very commonly used one is arc length, which is essentially a normalized gradient. However, you might also want to use curvature. So these are physical reasons. Alternatively, if you want to be kind of a bit more sophisticated, you might want to use a priori arguments. One of my favorite methods, and I've written many papers on this, is to use Lie group methods because a lot of the structures that you see in PDEs are dominated by Lie group symmetries, and you can use these to determine your function m. Or you can use simple a priori error estimates, and the ones that my colleague Wei-Zhang Huang tends to use are error estimates based on interpolation on the mesh that you get. Alternatively, you can you take the approach that Mark so splendidly spoke about this morning, which is to make some a posteriori error estimate with a primal dual method, or look for superconvergence. And these are the techniques that are used if anyone's used Colsys or Auto. This is what's going on in there. And finally, we might want to base M on data. If we're using it in data assimilation, we might want to use it to make sure that our correlations are well dealt with. So these are various approaches. The jury is out as to what's the right thing to do. The advantage of these ones is that they're very straightforward and simple to use and often do the job very well. These ones down here are obviously much harder to use, but may do the job even better. And there's lots of theorems out there that we need to prove. Certainly if you've got Lie group symmetries, I would always say go by this. So that's how we choose our monster function M. I won't speak any more about that. So how do we construct our mesh? Well, unfortunately, in 2 and 3, in 1 dimension, that equation I put down uniquely defines the mesh and everything is fine. But in 2D or 3D, if I was to say, give me a set with a fixed area, there's an uncountable number of sets that we can use. So that equidistribution equation doesn't tie down the mesh at all. That equation I put down has an uncountable infinity of solutions. And that means that one of the results of that is that when you look at the moving mesh literature, there's really quite a lot of methods out there competing for your attention. And here are just a few of them. The GCL method, harmonic mesh maps, tensor product equidistribution, the Winslow method, and sorts of things like that. There's quite a lot of literature out there. However, I think there's a good and kind of sensible way of closing the system, and that's to kind of use what we call optimally transported meshes. Now, we've had a lot of talks already comparing AMR with uniform meshes, and a lot of people have been saying uniform meshes are good, really good. And the reason uniform meshes are good is that they avoid long, thin regions and all that sort of stuff. So it's not unreasonable to say a measure of the quality of a mesh is how close it might be to a uniform mesh. Okay? So an optimally transported mesh is a mesh which satisfies that equidistribution equation that I put up earlier, but is also as close as it can be to a uniform mesh given that it solves that equidistribution equation. So I take all the solutions of the equation. Yes?
One clarification. Yeah. What is meant by equidistribution function here?
Equidistribution means that if you look at this, if you look at one of those little squares there, right, that will be mapped, say, to that square there, and you want the integral of our measure over that square to be the same as the area of that square.
Scale preservation.
Essentially scale preservation, yes. Okay, this picture here, this was a mesh I generated for a problem in nonlinear optics where we were trying to solve ring-type soliton solutions of the two-dimensional linear Schrodinger equation. You can see it's kind of nice, you get this kind of nice sort of radial sort of effect here. Okay, so this is what I'm going to try to do. I'm going to find meshes which are as close as possible to uniform because I suspect that these will avoid skewness problems and stuff like that, whilst at the same time equidistributing my measure. So this problem also goes back quite a long way. In fact, there's a very rich literature, particularly in the fluid dynamics community, and even richer literature in the economics community. And I'm going to choose as my measure of how close my mesh is to uniform by saying if this is my original point and I move to this point, I'm going to try to minimize the L2 difference between my uniform mesh in my computational domain and my moved around mesh in the physical domain. So I'm going to minimize this, and I'm going to minimize that subject to this condition here, which is this equidistribution condition, which is a beautiful nonlinear problem called the Monge-Kantorovich optimal transport problem. And I say it has a rich literature in fluid mechanics and economics and so on. So we can dig into that literature on using image processing as well. So we can dig into that literature to see what we can do about finding this. And as I say, I argue that by doing this, we're likely to get good meshes. And later on, I'll show that we absolutely do. Okay, so you dig into the literature. Unfortunately, Mike Cullen at the Met Office has an encyclopedic knowledge of the entire literature of the optimal transport system, which is unbelievably useful. And here's a key result due to Jan Brenier, which makes everything work. And the result is twofold. Firstly, that big nonlinear system I put up there has a unique solution. So we know there's a mesh out there, and we know it's unique, which is a very good thing. And secondly, Brenier shows a way to construct this, The map that we're interested in, this function f, from the computational to the physical domain, is the gradient of a convex function p. So we're going to call p the mesh potential, and the map that I'm interested in is then the gradient of this. And these things are kind of well known. They're called Legendre transformations, and people like Mike Sewell and Brian Hoskins and so on have used these transformations to study various types of meteorological phenomena, and particular frontogenesis type things. What's the advantage of this? Well, one of the things that's going on here is that if this function, this map that we're interested in, is the gradient of a scalar convex function, then if I want to generate a mesh in 2D or 3D or 365 dimensions, if I'm doing finance, all I ever need to do is solve a scalar equation. So these methods work just as well in 1D, 2D, 3D, or 365D. Okay, so let's have a look at this function p. So as I say, the function that I'm interested in computing is the gradient of p, and therefore the Jacobian, I'm doing it in 2D because in 3D it just looks messier. The Jacobian is the Hessian, it's the matrix of second derivatives of p, which is this, and so this becomes this, and therefore my mesh is obtained by solving the equation that the monitor function applied to the gradient of p times this nonlinear thing here equals 1, okay, which is a fully nonlinear elliptic PDE. Really horribly nasty beast. Okay. So at this point you start thinking, why am I bothering? All I wanted to do was solve a nice simple equation to start with, and you tell me to find the mesh, I have to solve something really nasty as part of the process, and that's quite a legitimate thing to say, and I'm going to have to try and convince you why it's worth doing this. But just to say one thing before we get on to that, one of the things I said about our adaptivity was because you're dealing with the whole mesh in one go, we can control quite a lot about the regularity, and what this boils down to is saying that both the global features of the mesh and local properties are related to properties of this function, the solution of this equation here. And again, there's this very rich literature that we can dig into to find these. So this is what we're going to solve. Okay, well let's think about this. So the basic idea is that to generate the mesh, once we know m, we solve this problem, and there's the good news. The equation has a unique solution. The bad news is it's a very, very hard equation to solve. Now the good news is that we don't need to solve it. Why do we not need to solve it? We are interested in computing the climate or the weather and so on. I don't give a damn about computing the mesh particularly accurately. Anything good enough is probably good enough. So I don't need to solve the mesh equations particularly accurately. Certainly to nothing like the accuracy I'm interested in solving the original equation. And so in practice all you need to do is set up some sort of relaxation process, iterate a few times, and you've got a good enough mesh to work. Okay, and I'll talk about that in a minute, and that gives you a very simple way of solving that equation. Alternatively, if you really want to solve it, a group at Los Alamos have developed some Newton-based and multi-grid-based methods for solving that equation. Exactly, personally I think that they are working too hard. Or you can go right back to the original literature on optimal transport and use that. But I'm going to take the approach that the most straightforward way to generate the mesh is to solve a relaxed form of the Monge-Ampere equation at the same time as you do everything else. Okay, so this is how it works. And the inspiration I got to do this was from the moving mesh PDE work of my great friend and collaborator Bob Russell in Simon Fraser University, Canada, together with former PhD student of mine, Jeff Williams. And what we do is we take a function q, which we're going to ultimately take the gradient of, which evolves towards the function p, which defines the mesh, and we solve this horrible mess, which is a evolutionary equation, and the solutions of this evolve towards the solutions of the underlying equation. And we're going to not solve this till we get to the final equation. We're just going to set it up as an explicit calculation, iterate about a few times, as long as we kind of feel we want to, and what we then get is probably a mesh which is good enough to do all our calculations on. This looks rather a mess. It has various bits and pieces to it. The thing on the left is a smoothing operator to smooth the mesh, which goes back to the seminal work of Tom Howe and Seneseris and that group. The thing on this is an averaging of the monitor. Chiara Piccolo again spoke a bit about this yesterday, and that thing there is just to make sure that the equation has global solutions. Okay, so this is the equation that we are solving to do our mesh. And you might say, well, that looks incredibly strange and complicated compared with the much more obvious and direct method of doing AMR, where you look at an element and if it doesn't satisfy a criteria, you halve it or something. And that's a perfectly reasonable objection. But in fact, this is quite a simple thing to do. You discretize it, you solve it explicitly, you solve it quickly, and you can generate meshes from this very, very straightforwardly, even in 3D, even on meteorological type problems. Okay, so how do we proceed now? Well, by the way, I call that the parabolic Monge ampere equation. So,
the Monge ampere equation itself, the solutions do exist, but they're extremely weak, aren't they? I don't understand it very well. Are the solutions to this equation smoother than you get?
Very, very good point. The regularity isn't great, but it doesn't have to be great. Again, we're interested in generating a mesh, not a solution. So I don't mind particularly if it's a bit weak. That doesn't really matter. And in practice, the regularity doesn't.
I was just wondering if this spatial smoothing term is trying to control that.
The main reason you have that is that when you discretize this operator, there's some real nasties around, and you want to make sure they don't grow when you solve it explicitly, and the spatial smoothing knocks out the nasties.
To make sure it does converge towards the solution.
Exactly, yes. It's knock out nasties. But you're absolutely right. The Monge ampere equation's got quite difficult smoothness. In practice, it tends to be second derivative, but not third. You have continuous second derivatives, but then you get a log term coming in which mucks up your third derivatives, but I can live with that. Good point. Okay, so there are basically two issues here. So firstly, let's imagine we're in a world where we know what M is. And we want to generate a mesh based on that. Then what you do is you take that parabolic equation and you solve it explicitly forward in time. You don't iterate to convergence, you iterate for as long as you feel you want to until you got close to mesh. And that's what you do. And as I say, we use explicit methods, explicit forward Euler. And for a meteorological problem, such as the one I'm about to show you, with a million or perhaps rather more than that mesh points, such as local area model, we can typically generate a 3D mesh in about 5 minutes. So this is joint work with Phil Brown and Chiara. And other areas where this might come in is sort of image processing and so on. So I'm going to show you some pictures now of the 3D meshes that we generate. And just to say, when we're doing meshes for data assimilation, it seems to be that taking a monitor function, which is an approximation and a scaled approximation to potential vorticity, actually works rather well. So here's one of the problems we're interested in. Here's the UK, there's Ireland, Scotland up there, Yorkshire there. This is the southwest where I live, and we've got a front coming in here, so that's a radar image supplied, thank you, supplied by the Met Office. Yes, it's always raining where we live, always. Do come visit us. So the Met Office have computed the background state for this problem, and then we wanted to kind of see what sort of meshes that we could get for that. So if we're looking kind of downwards at the moment, and I'm afraid this doesn't come out very well because the mesh is so fine that it doesn't really work too well on this. we've got a very, very fine mesh here, so you can't really see very well. This is looking down on the UK from above. It's exactly the same picture that we had for the radar. And this is a full three-dimensional calculation. And so we've taken a slice through that three-dimensional volume at the 16th level in terms of the Met Office's codes. And here's the front, so you can see the mesh points have been concentrated in towards the front. And there are various other features that are being captured as well by this. And so you can't see the mesh points because it's so fine. It's really quite a complicated calculation, this. Norway's up here, and the UK sort of sitting there, and Ireland's about there. If I take a line going up through here, and then take a cross-section through that, then the resulting mesh looks something like this. Here again, here's our front. You can see the front is actually not touching ground. It's a bit above ground. So here's the front being very well resolved by the mesh. Again, this is a two-dimensional section through this three-dimensional mesh. Height going that way, and we're going from north-south here. Here's another feature underneath the front, which we've got the mesh through, and various other features there. And you can see that the mesh, really kind of looks very nice, very regular, and is capturing this feature really very, very well indeed. So these are, say, calculations which my postdoc Phil did together with Chiara and Emily over in Simon Fraser University. And these are going to hopefully form part of some future data assimilation calculations at the Met Office. Okay. What am I doing? What am I doing? That's it, yeah.
So at every time step, you want it to move, you would recompute?
Not necessarily.
Oh, not necessarily.
Not necessarily. And I'll get onto that in a minute. So at the moment, all I've done is assume that we got a monitor function and had a look at the sort of meshes that you get. We're now going to move on to the next thing, which is to see what happens when we're actually trying to compute on that mesh. As I just said on advert, these are the sort of things that, again, you can do. This is some work I did with Tom Melvin and Nigel Wood, who are both, again, at the Met Office, of a collapsing bubble falling onto the ground. And this is the sort of thing that you get. And these are the sort of meshes that get generated. In this case, we use arc length. That's just a kind of quick advert. So, I want to say a few words before we get onto the process of calculating atmospheric flows about the nature of the meshes that you get. So firstly, these techniques are based on geometric properties, geometric ideas, and so the meshes that you generate typically have very nice geometry. So the solution, the Monge ampere equation, is an equation which is invariant under translations, under rotations, and under periodicity. So these methods are very good at generating meshes which have good rotational symmetry where you need it, good translational symmetry where you need it, and various other things. So here's a mesh that we generated by mapping a square into a circle, well, a truncated circle, just to make it a little bit more challenging. And again, it's one of these ring type things. And again, you can see it's got a very nice regular structure where you want it. Here's a mesh that we generated as part of a solution of Berger's equation, where we have a shock moving through the domain. And so here's the shock here, and the mesh has actually twisted itself and globally aligned itself with the shock. And we actually have a theorem, myself and Emily, that if you do have linear features in the problem, then the mesh will globally align with those linear features. So it's not a local patch, the whole thing shifts around and globally aligns. And so this is really very good for then doing calculations, and you can see these things are quite kind of nice and regular. And this alignment is a result of solving a PDE for the whole domain rather than just putting in local patches. So this is one of the features of our activity. Convergence, well, we've got this kind of relaxation property, and it's relatively easy to show that it's stable, so that if you iterate that equation for long enough, you will converge onto the mesh, and if you perturb away from it, you'll converge back to it. And that's basically because the Monge-ampere equation is the heat equation when you linearize it. Then various other things. If providing your equation doesn't change too rapidly, the mesh will faithfully follow it. This is the really important theorem. This is the one which took forever to prove. We can rigorously prove that the solutions of that relaxation process always lead to one-to-one mappings from the computational domain to the physical domain. What that means is that you cannot get mesh tangling. It doesn't matter how much vorticity there is in the solution, what nasty things are going on, you will always have one-to-one really nice meshes coming out of it. And this really took a lot of proving and required careful use of maximum principles and so on. Also, mesh points don't cross the boundaries, everything stays where you want it. So it's a very, very strong regularity result. Another result which I'm kind of also pleased with is that if your underlying problem has scaling symmetries, typically due to some sort of Lie group structure or something, and lots and lots and lots of PDEs have exactly this, then providing you choose your monitor function so that it kind of respects those symmetries, then the underlying meshes will automatically respect them as well. So basically we can build all the symmetry of the PDE into the meshes, and that means that we can get self-similar solutions, we can get Noether theorems, we can get conservation laws coming out automatically from the way we do our meshing. Okay, so that's kind of a bit about how we generate the meshes. What I want to do now for the sort of second part of the talk is to tell you about how we then couple those meshes to the solution of differential equations, which is of course...
Just quickly ask, so do all of those lemmas and things still hold even if your solution is approximate? Because you said you kind of don't go all the way in.
That's, no, well, I'm going to answer a different question. These all hold for the Monge-ampere equation,
right,
and the time-varying version of it. You don't solve the Monge-ampere equation, you solve the discretization of the Monge-ampere equation, and these properties all hold providing you have a sufficiently good discretization. So that's what you should have asked, and that's the answer to your question. Otherwise, they all hold for the full time-dependent thing. Yeah.
And is what you're doing sufficiently good? In particular, is only doing a few iterations?
You do enough iterations so that you're close enough. As I say, you don't. Let me give you an example. In the work that we were doing on these three-dimensional data assimilation-driven problems, we can generate a perfectly adequate mesh in 5 minutes. If we wanted to iterate to convergence, it would take between half an hour and 3 hours. Okay, and that's useless. I mean, that's ridiculous and too long for a simple calculation. 5 minutes is perfectly adequate to give you meshes. I mean, we could probably get it less than that if we tune things rather more. Okay, so of course, what we're interested in normally is not generating meshes. What we want to do in general is to solve a differential equation. And in that case, this function m will be a function typically of the solution of our differential equation. So it could be the potential vorticity of the equation, or it could be some error estimate, either a priori or a posteriori of the differential equation. So in other words, we've got to solve the equation and then do all that thing. When we want to discretize the equation, we have one great thing up our sleeve with this approach, in that we're going from a computational domain which has a beautifully regular uniform grid in it, mapping that into a physical domain. Where are we going to discretize? Well, best place to discretize is where everything is nice and uniform. So what we typically do when we do these things is we solve for the mesh, but always compute in the computational domain. And then because we know the function from the computational to the physical, we can get all our derivatives in terms of that function. And here they look a bit of a mess. But That's great. We can always work in a nice simple domain. Okay, so how do we couple? Well, there's two ways to couple. There's the elegant way, which doesn't work, and the non-elegant way, which works much better. So the elegant way is to say the Monge-ampere equation is a differential equation, or parabolic Monge-ampere equation is a differential equation. I want to solve, say, the Euler equations, they're differential equations. Put the whole thing together, we get a system of differential equations, and then we just go for it. And we just solve the whole lot. And in 1D, that works very well. If you want to solve parabolic problems, when there isn't much convection around, it works very, very well. And in fact, very, very well indeed. If you want to solve problems with lots of advection or convection or something, it seems to not work at all, and everything grinds to a halt. But this is an elegant method, and I'd very much like to try to get this to work for problems with advection because it avoids lots of problems with interpolation. But the somewhat less elegant but much more robust method is to kind of decouple the problem a bit. And basically the idea is this: you have some sort of mesh, which you know, you time march your PDE on that mesh to some new time. That gives you a new PDE, a solution of the PDE. You then plug that into your monitor function. You freeze the PDE and you evolve the mesh forward in time so that becomes then fitted to that PDE. And then you interpolate the solution of the PDE onto that new mesh. So this is kind of a fairly straightforward method, and you kind of repeat from this. And this is the method that people like Seneseris and Howe or Tao Tang and so on, or John Mackenzie and so on have used with to great effect. One of the advantages of this method is, as I say, it's very flexible. We can build in conservation laws, and particularly we can put pressure correction steps into this very well, so we can build in incompressibility. Disadvantage: that step's easy, that step's easy, that step's horrible. Okay, interpolation from one mesh to another to make sure you keep things like conservation of mass and other stuff, or geostrophic balance and so on, is really quite hard, and you have to work pretty hard at that step. So, but this method seems to work well enough. Okay, so let's give a couple of examples. So my first example is it's not a meteorological problem, but it's a problem which does kind of show some of the power of this method, which is parabolic blow-up. Ut is the capacity U plus U cubed. This is a crude model of combustion. We heard a talk, I think it was yesterday or maybe the day before, that people are interested in blow-up of the equations of vorticity. Of course, we all want to show that the Euler equations in 3D blow up in finite time, because then we get $1 million or whatever. Here's an equation which definitely does blow up in finite time. It develops a singularity at a finite time capital T. And as it develops that singularity, so the smallest length scale in the problem shrinks down to essentially nothing. The monitor function we use is based on Lie group ideas and works out to be this funny thing here. If you want me to say why, I take about an hour to explain that. But anyway, that's the monitor function. Works very well. And these are the sort of results that you get. This is a computation with this method. Here's the original data, which is a Gaussian of height 10. If you let that go and wait for a bit, then the solution comes up to a value of about 10 to the 5. The singularity has a width of about 10 to the minus 5. So if you want to capture that with get any detail at all with a uniform mesh, we need 10 to the 5 points in both directions. In other words, 10 to the 10, an awful lot to be able to do that. With the methods that we use, you can capture that perfectly adequately with about 100 points. So there is a factor of 10 to the 8. Now, I think it was Matt was saying if you get a factor of 10, you're doing well. There we are, 10 to the 8. These are the meshes that you generate. I don't know how well you can see it, it's a bit light. This is the mesh that's generated to get that singularity. And if you take that bit there and you expand it, it's beautifully regular. There's no skewness. It's as regular as you want, and that is a direct consequence of the regularity properties of the Monge ampere equation. This is what the solution looks like in the physical domain with this whacking great singularity. What does the computer see? That's what it sees. That's what the solution looks like in this computational domain, which, as I say, is where you should do your calculations. Regular as hell, length scale 1. Job done. Okay, so we kind of test these methods out and explain. One of the reasons we use these as test problems, again, Hilary was talking about the need to have test problems for which we have analytic solutions. We don't have an analytic solution of this problem, but there's an awful lot of asymptotic theory associated with it, so we can use that asymptotic theory to test. Now, this isn't a proper problem, of course. Let's talk about a proper problem. So the example I'm going to use is an example that Mike Cullum suggested, and if anyone's interested, you can look at it in his book on atmospheric flows and so on. And this is the ED problem, which is a two-dimensional vertical slice approximation to the geostrophic equations. So what is the ED problem? There it is. That's the ED problem. It's involving U is the U and V are horizontal speeds, wind speeds, W is vertical wind speed, theta is temperature or potential temperature, and it's incompressible in the UW coordinates, and you've got various other bits and pieces floating around. Phi is essentially the pressure term there. And this is an interesting problem because all the evidence is that this system here, given suitable initial data, does develop singularities in finite time. So just like the parabolic problem I put up earlier, which develops these singularities, if you run it for about 6.5 days, then we get a singular type of behavior forming. Okay, so this is a severe test for any method.
In the SG limit, you get discontinuity.
Absolutely, absolutely, very much so. And that's where we assume, as you get it in the SG limit, if you pull back from that, you still get it. Okay. Yes, I agree. Okay, so how do we discretize this? Well, the monitor function that we use is based on our old friend, potential vorticity. So we take the PV matrix and take the largest eigenvalue of that. Because we're always computing in the computational domain, everything's regular as hell. It's nice and simple. We can just use finite difference. So we use finite difference on a Charney-Phillips mesh in the computational domain with a pressure correction step at each iteration to enforce incompressibility. Interpolation work like the clappers to make sure that when we interpolate from one mesh to another, we keep our mass conservation and any geostrophic balance that we want. In answer to your question, the typical time step for the ED problem is a 10-minute in physical time step, at least in the initial stages of the evolution, and we typically update the mesh every hour. So we do 6 time steps and update. As the singularity is approached, so we reduce the time step, and we still update the mesh every 6 time steps, but we would keep the time step smaller as we approach the singularity. So let's have a look at the solution. What I'm going to show in the top line, this is the solution on the uniform mesh after 5 days. That's U, V, W, and theta. This is the solution on the moving mesh. So you can already see after 5 days something seems to be forming about here. This is our singularity starting to form along this line. It's not particularly sharp after 5 days. After 6 days, in the adaptive mesh here, we're beginning to see a very sharp singularity here. Something, you can't really see, there's something going on, but not much in particular. After 6.3 days, the adaptive mesh really has caught the structure very, very well, whereas the non-adaptive mesh is sort of vaguely thinking about it, but it isn't as well as you'd like. rather more revealing is that if we take a cross section through that singularity after 3 days, 4 days, 5 days, and 6 days, the blue curve is the computation with the adaptive mesh. The red curve is the computation with the uniform mesh. Sorry, those are the wrong way round. Apologies for that. Blue should be adaptive and red should be uniform. And you can see that it's really much, much better resolved. I mean, there's just no comparison really between the resolution on those two. So that's with 60 mesh points. And what's kind of interesting is that if you increase the resolution on the uniform mesh, the whole thing starts to oscillate and you lose everything. So the adaptivity really seems to be important, not just for resolving things, but also keeping things stable. If we have a look at the meshes themselves, on the left, this is the mesh after about 3 days, and on the right, this is the mesh after about 6 days. So you can see over here, it all looks pretty regular. Over here, it looks regular, but we're clearly clustering points along that singularity forming, which is where we want them. And if we have a look around here, which is where the action is, that's what the meshes look like, where the action is. As you can see, they're really very regular. There's no real hint of skewness here. So this is a tiny length scales over here, but everything looks kind of regular. And if you don't believe me, there's a skewness measure. If lambda 1 and lambda 2 are the eigenvalues of the Jacobian, then this is a canonical measure of the skewness. It basically tells you if a square is mapped to some sort of parallelogram, how skew that parallelogram is. So, sorry, I should have divided by that. 1 is basically non-skew at all, and log big is skew. And this measure, this is again, here's my singularity, but the skewness of the mesh, its maximum skewness is 1.4, which I can live with easily. Okay, there's no problems there at all. And it's hardly varying very much from 1. And skewness is again this quantity here, trace J transpose J over det J, is something you can actually find bounds for, provable bounds in terms of solutions of the underlying Monge ampere equation. So just to conclude, so firstly, my first point is that our adaptivity is a reasonable way to go, and if you're going to go that way, optimal transport and Monge ampere is a kind of natural way to do it. Secondly, that these fast algorithms that we use seem to work well enough. Thirdly, that it seems to work quite well for a variety of problems. There's lots and lots of problems that we haven't tried it on, which again is something I hope will come out of this 4 months workshop. Will be some really good test problems that we can throw this at and see whether it really does work properly. It's looking good, but I say there's lots of work to do to compare its effectiveness. In particular, I want to, during this program, put in a lot of effort into comparing it with the tried and tested AMR methods that we've been seeing the last few days, and I will say that may be a good project for this program. At that point, I'll finish.
Very nice and nicely on time. Questions? John?
Well, this was very interesting, very nice. But there's one step that I just didn't catch. Maybe I'm getting slow with age. It's the Russell reference where you have
yes, Bob Russell.
Yeah, the equation that you're solving.
Yes. I'll tell you about the history of this. So Bob Russell, working with various colleagues, was looking at moving mesh generation in 1 dimension. And to do moving mesh generation in 1 dimension, he again wrote down the map from the computational domain, which was just the unit interval, into the physical domain, which was another interval. And he developed a differential equation for that map, which he called a moving mesh partial differential equation to define the mesh. And that was basically taking the equidistribution equation in 1D and then adding a relaxation term onto it. when we were looking at generalizing that into 2 and 3D, what we basically did was to take his approach and take the equidistribution equation, which now was the Monge ampere equation, and add a relaxation term. So that was our inspiration. And in fact, the method that I described in one dimension is a combination of 2 of Bob Russell's methods kind of glued together. So that's what the inspiration was of that relaxation term. To answer your question.
Okay, well, maybe we can discuss
Yeah, sure.
Dr. Cotter.
And the E problem, it's my
Yeah.
favourite problem. The rigorous results about the singularity forming are only in the SG limit.
I agree, yes.
But do you actually? So I'm very interested. If you do, you actually observe a real singularity in
Okay, so
the Boolean S?
again, absolutely brilliant, super. Just on that question, agreed. There is no rigorous result. This isn't. I'd say I should have put observed or conjectured.
But can your method kind of tell you a singularity is it really is going to? Do you see some scaling or something like that? Some occurring?
Okay, so again, this is something I'm very interesting. There is every indication from the numerical work that it is getting steeper and steeper and steeper. There isn't at the moment, although I'm working on it, asymptotic theory to say if there was a singularity what it would look like.
Mm-hmm.
I had a long chat with Tom Howe about this. I mean, this is okay. I should put conjectured or something like that. I agree absolutely. In SG limit, we know what's going on, but this isn't an SG limit.
And can you integrate past that time? So because Mike's challenge is to get the to see it come back again after, because the SG solution still exists.
Okay, so let me say where we are at, and again, this is continuing to be collaborative work with Chiara Piccolo. You can't go. There is real singularity, so something's got to give. So essentially, you have to put some diffusion in to get beyond the singularity. Now, if you put diffusion into the uniform thing, then you can get past it, but eventually things go doink. And this is work that ongoing at the moment. What we believe is that we can, with the adaptive methods, get through it with a much smaller amount of diffusion added. But at the moment, we haven't been able to do it, so that's a problem we're working on at the moment. So see if we can get through. And
so your idea is that you would switch on some very local diffusion near where the front is.
Correct.
And carry on.
And then carry on. So you've got to put something in because you genuinely have a singularity. I mean, you've got no numerical method that I know of would be able to get you directly through that. But yeah, so what we want to do is switch on a small amount of diffusion, get through, but much less diffusion than we. If you put the diffusion into the uniform thing, it will get you through, but eventually goes beyond. But yeah, absolutely. I mean, this is exactly the point. This is what Mike wants. So as far as Mike's concerned, I haven't solved the problem at all. But it's ongoing work.
Moving back to your the coupling between the two problems.
Yeah.
Is there an alternative strategy in there where you would? So I'm thinking about the second mode where the problem is the fact that you have to do interpolation. I agree that's easy.
Yeah.
Could you do it in an ALE type way? Could you say really moving the thing and then put the terms in the equations and have it event through the?
That's a little bit like the first method, but this is the ALE method is something Mike Baines has worked through and got going. Yeah.
Okay, so that works too. Yeah. Cool. I guess we should probably move on, which makes me very excited because we're going on to my favourite subject, which Bardo is going to talk to us about.